Welcome to day one of the automation integration portion of this class. So my name is Bill Perkins. I've been working with TRC for a little over a decade now in the SCADA and automation and integration world. And today's presentation is going to cover automation and integration as it relates to protective relaying. We're going to be talking about SCADA, which is an acronym for Supervisory Control and Data Acquisition. We're also going to be talking about SCADA as it relates to protection and control, as well as the overlap that SCADA has with system protection. And then we're going to finish off with network and serial connectivity. All right, SCADA. As I mentioned, supervisory control and data acquisition. We're going to come back to this, but notice that the acronym SCADA is made up of two terms: supervisory control and data acquisition. So SCADA systems are designed to safely and reliably monitor and control the operation of large electrical networks. It does this by collecting and processing data from other substations, providing operators with a comprehensive view of the entire network. So what you'll notice is this diagram's broken up into two different sections highlighted by these yellow boxes here. The lower section focuses on multiple variations of SCADA systems that you would encounter in the power utility world. And the upper section lays out a typical energy control center, or ECC, which includes the SCADA server. These two sections are connected via a communication link, which can be anything from phone lines to direct fiber to radio or microwave or any combination of these. So as you can see, we have four different variations, one of which the intelligent electronic devices, which can be protective relay or a phaser measurement unit, is serially connected to a port server or COM processor and communicates directly to the ECC without a data concentrator. Another setup in which would be seen at a smaller station or located in a roadside cabinet, where we have a remote terminal unit connected to IEDs and concentrating data to a local terminal unit as well as the ECC via some form of communication link. This variation is your typical substation communication architecture that has an RTU, multiple IEDs, as well as a local HMI, which is a human machine interface. The IEDs here are shown networked to this RTU via a local area network, which we'll discuss later on in the presentation. The RTU is gathering information from all of these IEDs and is concentrating all of that data so that it can send to either the local HMI or send through the communication link to the ECC, which contains the SCADA server. The last variation we have utilizes PLC, which is a programmable logic controller, instead of an RTU. A PLC is very similar to an RTU, but more focused towards process control and industrial equipment. You will find PLCs in a power utility substation, but they're much less prevalent than RTUs, which are typically built and designed specifically for the utility environment. So, so these are just a few variations, but we'll give you a broad understanding of different architectures used in the SCADA system. So within a typical substation, as it relates to SCADA equipment, we have different devices. as mentioned on the previous screen, that's utilized. Um, One of them is an RTU, which is your remote terminal unit. This is basically the brains of the SCADA system, where it will interface all of your IEDs as well as your hardwired I/O input and output for any devices that aren't intelligent. So this could be like a door alarm where a door opens and closes and hits a contact that would go directly into hardwired I/O and get transferred to the RTU in order to concentrate that data to the ECC. The um, the RTU will be specifically programmed or configured based on the needs of the utility. We'll talk about this more specifically in later presentations. The RTU will also concentrate the data and send it to the HMI, which is the human machine interface. This is typically an on-site screen that's used by operators where it displays all of the information about the substation. And you can have HMIs that are very detailed where every single bit of information is displayed, or HMIs that only show minimal but specific information. Um, in this case, the HMI that's being shown here with its graphical interface has many different screens that can be accessed by the operator to dig down deeper into the station uh, to see information that's necessary to the operator. The screen shown here is called a station one-line screen. It's a high-level overview of the station, and it shows breakers, status, bus voltages, line, uh, analog values, as well as distribution circuit analog values. So this screen gives the operator a good understanding of the overall status of the station. So if the operator wants to see more detailed information, they can click on one of these buttons at the bottom or click on the device itself to bring up specific information as to if the breaker is open or closed, if there's reclosing enabled in the relay, if the relay has communication issues, if permissive is on or off for bus protection, and so on. Um, as mentioned, these screens can be as detailed or minimalistic as the utility requires based on their specific needs. So what does automation and integration typically pertain to? What does a SCADA engineer typically do on a day-to-day basis? So as a typical SCADA engineer, you're responsible for RTU configurations. This entails setting up the RTU so it properly communicates to all the IEDs on sites, and is pulling all the proper data out of the IEDs in order to communicate the station status to the HMI or the ECC. The HMI configuration, which we've seen on the previous screen, that's building all of those screens, making sure everything animates properly, getting all the proper analog values to display on the screen and scaled properly, making sure the correct device statuses or alarms display properly on each screen, and so forth. These are just quick examples, but a lot of design thought goes into each screen in order to properly inform the user about the station. The next thing is network configurations, which we'll touch on later in the presentation. But within your substation, communication often occurs via networks, network switches, and they need to be configured properly in order for all devices to properly communicate. SCADA engineers will also do on-site commissioning of all the RTU configurations, the HMI configurations, and network switch configurations that have been designed and developed, and test to make sure that it all functions properly. And once local or on-site commissioning is complete, the SCADA engineer will also do remote commissioning, which is testing all the communications with the ECC. This will typically involve the SCADA engineer talking directly with the ECC representative and physically bringing in station alarms and analogs so the ECC can confirm all their remote data is accurate.
All right, so we have a video here that's going to go over SCADA systems as it relates to the electrical power industry.
The Lucy switchgear SCADA system is designed to safely and reliably monitor and control the operation of large electrical networks. The system collects and processes data sent from other substations, providing the operator with a comprehensive view of the whole network. This typical example shows a SCADA-monitored electrical network providing electricity from a primary substation to a range of regional consumers. The primary substation provides a feed out to a residential area, a commercial city district, and the local airport via other local substations. A busy port and a small rural community are also supplied by the primary substation through another circuit. Let's see how the SCADA system is used to manage and maintain the network during a fault. On a remote rural section of the network, a fallen branch causes damage to the overhead power lines feeding substation 2. This break in supply causes the circuit breaker for this line to trip at the primary substation, leading to a total power outage to both the port and the rural community that rely on this circuit. Power to the rest of the network remains unaffected. The SCADA system receives notification of the circuit breaker trip, then uses the fault passage indicators positioned around the network to determine where the fault has occurred. In this case, the fault passage indicator at substation 2 has not tripped, so at the remote SCADA data center, the operator is informed that the fault must be somewhere on the line between the primary substation and substation number 2. The operator can now use the Lucy switchgear SCADA system to isolate this area and reroute power to customers without a supply. The operator remotely opens the incoming switch from the primary substation to substation 2. And then opens the outgoing switch from substation 2 to the rural community. This totally isolates the fault area from the rest of the network. The operator can now close the outgoing switch at substation 3 to re-energize the link to substation 2. Substation 2 can now reinstate the supply to the port. In order to avoid overloading one side of the network, the operator chooses instead to close the GX switch on the backfeed to the rural community to reinstate their supply. Supplies to all affected areas are now complete, and the faulty line is safely isolated from the network, allowing the operator to arrange for a repair. Typically, the network will be sectionalized and power rerouted within 3 minutes of the original fault. SCADA enables the operator to direct the repair team to the specific area of the network at which a fault has occurred. Once the operator has confirmation that the repair is complete and all maintenance crews are clear of the area, SCADA can be used to restore the system to its usual operation. The newly repaired line is tested first by closing the primary substation's outgoing switch to substation 2. The line energizes as normal, confirming the repair. The operator can now close the incoming switch to substation 2, reinstating the original supply route. The backfeed from substation 3 is no longer required, and so the SCADA operator can open its outgoing switch. With the load removed from the lower side of the network, the rural community outgoing switch from substation 2 is closed, creating a parallel circuit for the area. The final step for the SCADA operator is to reopen the GX switch to disable the backfeed to the rural community, restoring the standard operation of the whole network. The Lucy SCADA system works in conjunction with our complete range of switching and protection solutions to provide operators with unprecedented control and management of their networks.
All right, moving on to the automation side of protection and control. So there's a significant overlap between the role of the A&I group and the P&C group, including the specification of ID communication ports, network switches, communications, and other hardware. As you can see in the picture here, the P&C group will specify the relay, but will interact with the A&I group to specify what type of communication ports are necessary for comms. For example, the A&I engineer will specify if it's a serial interface, if it's a network interface, if the communication medium is copper or fiber, and if it's single mode or multi-mode, and so on. And then in the bottom picture, you'll see that there are network switches, and the A&I engineer will specify what type of switch will be used, as well as what type of communication interface is needed, serial, fiber, etc. Also, the picture to the right, here showing the fiber patch panel. The automation and integration group will also specify the type of fiber patch panel and also the fiber ports needed. Are they ST ports, LC, SC type of ports, and again, single mode or multi-mode. The top portion of the picture here, you can see an RTU with a DB9 serial ports on the back. This setup is actually converting a DB9 serial interface to fiber. So the A&I group will typically specify what type of converter is necessary in order to convert the DB9 serial interface to fiber. And on the left here, we've got a pretty good overview of a SCADA cabinet, which we can see some 2411s at the top, which are typically taking in your hardwired inputs and possibly providing outputs. Below that is your HMI for the operator to interface with the station. Below that, we've got some network switches for creating a local area network, which we'll talk about later in the presentation. Next, we've got a GPS clock, which we haven't talked about, but basically receives timing from satellites and provides accurate time to all the devices within the station. Below that is your HMI computer, and then below that is your RTU. All of this information is often detailed on an integration one-line drawing. So the integration one line is one of the more important design documents for an automation and integration engineer. The one line shows all the major A&I equipment, such as the RTU, the HMI, the network switches, the GPS clock, and all of the IEDs, as well as what type of cables connect them to each other. The integration one line is the master roadmap for all the communications within the substation and lays out how everything is connected and how it's communicating. The A&I group will often do a cross-discipline review of this drawing with a P&C group to confirm devices for the design. So from within this integration one line, you can see some familiar devices that we've talked about so far. You can see the control house RTU. You can see some IEDs. You can also see the HMI touchscreen monitor as well as the HMI computer. We've got some Ethernet switches and an Ethernet router, which we'll go into more detail later. But again, this is the high-level design documentation that the automation and integration engineer will use for communications within the substation. This document will lay out how the RTU is configured, how the IEDs are configured, how the HMI is configured, as well as how the network switches are configured. So during the PNC design, relay part numbers must be specified in order for the relays to be properly purchased from the manufacturer. The portion that the A&I group works with is typically the communication ports, shown here in yellow. This is a typical SEL part number map that allows you to specify the relay as well as what type of communications the relay has. So for this example of SEL 2411, we can see that the slot B Ethernet port is a dual 100 base FX LC, meaning that it has 2 fiber LC ports that can support data speeds of up to 100 megabits per second. We can also see that this relay communication port is capable of communicating via DMP3 protocol. The part numbers associated with that are on columns 16, 17, 18 are 0, 8, 3. So other options that can be selected for the ports are, instead of a fiber Ethernet interface, this relay could have a fiber optic serial port. So instead of copper DV9 ports that we've seen previously, this could actually be a fiber interface that communicates using serial. The other option is slot B could have an iRig connector, which is a specific interface for time sync, which is typically provided by the GPS clock. And in newer substations, instead of having EMP3 protocol, you could have what's called IEC 61850. This is a more recent protocol that's been developed specifically for communications over a network or local area network. Again, this is just a quick example of how the A&I group would interface with the PNC group in the design. All right, so we've talked about how A&I interfaces with the PNC group. The A&I group also will interface with the system protection group, which does all the configurations for relays and IEDs. So as it relates to the overlap between the two groups, the A&I group will help with the configurations of the port settings within the relay. This will be letting the system protection group know if it's serial communications, and if so, is it a DMP3 protocol, and what's the address, baud rate. If it's a network port, we'll let them know the IP addressing, and other significant part of the interaction of the A&I group is to let the system protection team know what the actual point mapping is between the relay or IED and the RTU. This would include letting them know which relay points are going to be sent to the RTU and in what order. The A&I group will also work with a system protection group to work out relay logic related to alarms, statuses, and controls, which are passed through the relay to the RTU or HMI. We'll go into more detail about the actual point mapping and the relay logic in the next class, but for now, this is a high-level description of the overlap between A&I and system protection. So So again, this is just a quick overview of what you would typically see for network and serial connectivity on the back of relays or IEDs. In both photos, we can see similar connections just shown on different relay types. Both pictures show a copper Ethernet connection on the left side of the relay. This is a Cat5 or Cat6 cable with an RJ45 connection into the back of the relay. Each relay also has a fiber serial port with multi-mode fiber and ST connectors. And we can also see these relays have a copper serial connection with a DB9 connector. Just looking at these pictures here, it's almost impossible to tell how these interfaces connect with the overall SCADA system. But that's where that integration one-line drawing would come into play. The integration one-line diagram would show where all of these connections are going and kind of give us the big picture as it relates to their communication paths. All right, so next we're going to watch a YouTube video from Khan Academy about different types of communication.
My name is Tess Winlock. I'm a software engineer at Google. Here's a question. How does a picture, text message, or email get sent from one place to another? It isn't magic. It's the internet, a tangible physical system that was made to move information. The internet is a lot like the postal service, but the physical stuff that gets sent is a little bit different. Instead of like boxes and envelopes, the internet ships binary information. Information is made of bits. A bit can be described as any pair of opposites, on or off, yes or no. We typically use a 1 meaning on or a 0 meaning off. Because a bit has two possible states, we call it binary code. 8 bits strung together makes 1 byte. 1,000 bytes all together is a kilobyte. 1,000 kilobytes is a megabyte. A song is typically encoded using about 3 to 4 megabytes. It doesn't matter if it's a picture, a video, or a song, everything on the internet is represented and sent around as bits. These are the atoms of information, but it's not like we're physically sending ones and zeros from one place to another, one person to another. So what is the physical stuff that actually gets sent over the wires and the airwaves? Well, let's look at a small example here of how humans can physically communicate to send a single bit of information from one place to another. So say that we could turn on a light for a 1 or off for a 0, or use beeps or similar sort of things of like Morse code. These methods work, but they're really slow, error-prone, and totally dependent upon humans. What we really need is a machine. So throughout history, we've built many systems that can actually send this binary information through different types of physical mediums. Today, we physically send bits by electricity, light, and radio waves. To send a bit via electricity, imagine that you have 2 light bulbs connected by a copper wire. If one device operator turns on the electricity, then the light bulb lights up. No electricity, no light. If the operators on both ends agree that light on means 1 and light off means 0, then we have a system for sending bits of information from one person to another using electricity. But we have a problem. Let's say that, we want to send 5 zeros in a row. Well, how can you do that in such a way that either person can actually count the number of zeros? Well, the solution is to introduce a clock or a timer. The operators can agree that the sender will send 1 bit per second, and the receiver will sit down and record every single second and see what's on the line. To send 5 zeros in a row, you just turn off the light. Wait 5 seconds. The person on the other end of the line will write down all 5 seconds, say 0, 0, 0. And for ones, do the opposite. Turn on the light. Obviously, we'd like to send things a little bit faster than 1 bit per second, so we need to increase our bandwidth, the maximum transmission capacity of a device. Bandwidth is measured by bit rate, which is the number of bits that we can actually send over a given period of time, usually measured in seconds. A different measure of speed is the latency, or the amount of time it takes for 1 bit to travel from one place to another, from the source to the requesting device. In our human analogy, 1 bit per second was pretty fast, but kind of hard for a human to keep up with. So let's say that you want to actually download a 3 megabyte song in like 3 seconds. At 8 million bits per megabyte, that means a bit rate of about 8 million bits per second. Obviously, humans can't send or receive 8 million bits per second, but a machine could do that just fine. But now there's also a question of what sort of cable to send these messages over and how far the signals can go. With an Ethernet wire, the kind that you find in your home or office or school, you see really measurable signal loss over just a few hundred feet. So if we really want this internet thing to work over the entire world, we need a different way of sending this information really long distances. I mean, like across an ocean. So what else can we use? Well, what do we know that moves a lot faster than just like electricity through a wire? Well, light. We can actually send bits as light beams from one place to another using a fiber optic cable. A fiber optic cable is a thread of glass engineered to reflect light. When you send a beam of light down the cable, light bounces up and down the length of the cable until it is received on the other end. Depending on the bounce angle, we can actually send multiple bits simultaneously, all of them traveling at the speed of light. So fiber is really, really fast. But more importantly, the signal doesn't really degrade over long distances. This is how you can go hundreds of miles without signal loss. This is why we use fiber optic cables across the ocean floors to connect one continent to another. In 2008, there was a cable that was actually cut near Alexandria, Egypt, which really interrupted the internet for most of the Middle East and India. So we take this internet thing for granted, but it's really a pretty fragile physical system. And fiber is awesome, but it's also really expensive and hard to work with. For most purposes, you're going to find copper cable. How do we send things wirelessly? Wireless bit sending machines typically use a radio signal to send bits from one place to another. The machines have to actually translate the ones and zeros into radio waves of different frequencies. The receiving machines reverse the process and convert it back into binary on your computer. So wireless has made our internet mobile, but a radio signal doesn't travel all that far before it completely gets garbled. This is why you can't really pick up a Los Angeles radio station in Chicago. As great as wireless is, today it still relies on the wired internet. If you're in a coffee shop using Wi-Fi, then the bits get sent through this wireless router and then are transferred to the physical wire to travel the really long distances of the internet. The physical method for sending bits may change in the future, whether it's lasers sent between satellites or radio waves from balloons or drones, but the underlying binary representation of information and the protocols for sending that information and receiving that information have pretty much stayed the same. Everything on the internet, whether it's words, emails, images, cat videos, puppy videos, all come down to these ones and zeros being delivered by electronic pulses, light beams, radio waves, and, lots and lots of.
So referencing back to one of the first slides we looked at, I kind of breezed over the communication link portion of the drawing. But in this slide, we can dig a little deeper into what that actually is. So in order for the SCADA system to communicate back to the SCADA server, there has to be some sort of communication medium. That communication medium can either be hardwired via telco circuits, which is a combination of modems and telephone cables, or it could be a fiber network connection with a direct path from the RTU to the ECC, or a fiber ring utilizing multiplexers, which gather all the communications at remote locations and condense these communications onto a single fiber ring, which will route the RTU traffic directly to the ECC and SCADA servers. Another widely used communication method is radio or microwave, which allows the RTUs to communicate in locations where physical telco or fiber cables can't be installed. In some instances, a combination of all of these communication methods can be utilized, such as an RTU in a remote location will use radio or microwave to communicate back to a location that has a multiplexer. in which those communications will then be transferred to the multiplexer ring in order to communicate back to the ECC. Or another example would be a telco circuit is used for a short distance and then transferred to radio or microwave and then sent to the ECC that way. Either way, each method of transmission obviously has its pros and cons, but is carefully studied by the telecom engineers to decide the best solution. So I briefly touched on this earlier, but I wanted to go into more detail here about network and serial connectivity. So there are multiple ways that IEDs or devices can communicate within a substation. One of the ways is via a serial connection, which is typically a point-to-point connection. So an IED would have a DB9 serial or a fiber serial connection and would connect directly back to the RTU that way. Or in other instances, there is a local area network, which is comprised of either a single switch or multiple switches, which IEDs utilize their network ports to talk back to the switch, in which the switch is then connected to the RTU. So within the local area network, the IEDs also have the ability to communicate to all the other devices that are on the network. Within the IEC 61850 protocol, that method of communicating to all of the IEDs at the same time is utilized. But in a non-61850 network, which is considered a conventional system, it's usually just the RTU communicating through the LAN directly to the IED that it wants to communicate to. So in this drawing here of the one line, we can see the Ethernet switch here in the middle, communicating to or connecting to all of the IEDs in the station, as well as yard IEDs. So these could be transformer relays or breaker relays, which are connected via fiber and fiber patch panels to an Ethernet switch and up to a router and then down to a switch. So within a local area network, the Ethernet switches are usually communicating just to the local devices. And the router is there to connect to all of your external communication sources. So local area network, which is a LAN, and then your WAN is your wide area network, which would be your external communications to your ECC and SCADA server. In a few of the slides, I've used the term network or Ethernet and serial, and I kind of just wanted to go over some of the differences between them. So Ethernet or network connection will typically have an IP address, which is a logical address that identifies a device on a network, as well as an IP port, which is a virtual protocol specific port number that tells the device which program it needs to use. We've got a video coming up after this, which will go into more detail about IP addresses and IP ports. But basically, the IP address tells the info which device to go to, and the port number tells the device which program to use to interpret the information. Serial connections are a little more straightforward in that they're mostly a point-to-point or point-to-multipoint connection. And the info within the packet just needs to know what physical port it's going to and at what speed, which is called the baud rate. Typical rates in bits per second are 4800, 9600, 19200, or 115,200. Here we have a close-up with what your typical network ports and serial ports look like. So in this picture, the network ports are RJ45 connections, and the serial port is a DB9 connection. All right, we have another video from Khan Academy that goes into a little more detail about IP addressing and networking.
My name is Paula, and I am a software engineer at Microsoft. Let's talk about how the internet works. My job relies on networks being able to talk with one another. But back in the 1970s, there was no standard method for this. It took the work of Vint Cerf and Bob Kahn to invent the Internet Working Protocol to make communication possible. This invention laid the groundwork for what we now call the Internet.
The Internet is a network of networks. It links billions of devices together all around the globe. So maybe you're connected with a laptop or a phone through Wi-Fi, but then that Wi-Fi connection connects to an Internet Service Provider, or ISP, and that ISP connects you to billions and billions of devices around the world through hundreds of thousands of networks that are all interconnected. One thing that most people do not appreciate is that the internet is really a design philosophy and an architecture expressed in a set of protocols. A protocol is a well-known set of rules and standards that, if all parties agree to use it, will allow them to communicate without trouble. How the internet actually physically works is less important than the fact that this design philosophy has allowed the internet to adapt and absorb new communication technologies. This is because in order for a new technology to use the internet in some fashion, it just needs to know which protocols to work with. All the different devices on the internet have unique addresses. An address on the internet is just a number, similar to a phone number or a sort of street address that's unique to each computer or device at the edge of the network. This is similar to how most homes and businesses have a mailing address. You don't need to know a person to send them a letter in the mail, but you do need to know their address and how to write the address properly so the letter can be carried by the mail system to its destination. The addressing system for computers on the internet is similar, and it forms part of one of the most important protocols used in internet communication, simply called the Internet Protocol, or IP. A computer's address then is called its IP address. Visiting a website is really just your computer asking another computer for information. Your computer sends a message to the other computer's IP address, and it also sends along its origin address so the other computer knows where to send its response.
You may have seen an IP address. It's just a bunch of numbers. Numbers are organized in a hierarchy. Just like a home address has a country, a city, a street, and a house number, an IP address has many parts. Just like all digital data, each of these numbers is represented in bits. Traditional IP addresses are 32 bits long, with 8 bits for each part of the address. The earlier numbers usually identify the country and regional network of the device. Then come the subnetworks, and then finally the address of the specific device. This version of IP addressing is called IPv4. It was designed in 1973 and widely adopted in the early 80s and provides for more than 4 billion unique addresses for devices connecting to the internet. But the internet has turned out to be much more popular than even Vint Cerf imagined, and 4 billion unique addresses won't be enough. We're now in the middle of a multi-year transition to a longer IP address format called IPv6, which uses 128 bits per address and provides over 340 undecillion unique addresses. That's more than enough for every grain of sand on Earth to have its own IP address.
Most users never see or care about internet addresses. A system called the Domain Name System, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like,
Hi there, I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, you know how to get to code.org?
I got it right here. It's 174.129.14.120.
Oh, okay, great, thanks. Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you wanted.
Awesome, thank you.
So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is DNS spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet is huge and getting bigger every day, but the domain name system and internet protocol are designed to scale, no matter how much the internet grows.
All right, so we're not going to go into too much detail about the OSI model, but I just wanted to make sure that everyone was familiar with it and know it exists. So the OSI model is a model that describes the 7 layers that a computer system would use to communicate over a network. The first 3 layers are your media layers. So layer 1 is your physical layer. This layer deals with the physical transmission of data over a network medium, such as a cable or a wireless signal. It defines the characteristics of the physical connections and the transmission of raw bytes. So layer 2 is your data link layer. This layer is responsible for providing reliable data transfer on top of the physical layer. It's responsible for packaging and unpackaging data frames between network devices and detecting and correcting transmission errors. Layer 3 is your network layer. So this layer is responsible for routing packets to the correct destination. It uses network addresses such as the IP addresses we talked about to identify devices on the network and routing protocols to determine which path a packet should take. The last 4 layers are your host layers, with layer 4 being your transport layer. This layer is responsible for providing reliable data transfer between the two applications. So it ensures that packets arrive in the correct order and controls the flow of data to avoid network congestion. Layer 5 is your session layer. So this layer establishes, manages, and terminates sessions between applications on different computers. It provides services such as authentication, authorization, and error recovery. Layer 6 is your presentation layer. This layer is responsible for formatting the data for use by the application. It can encrypt and decrypt data, as well as convert data formats. Layer 7 is your application layer. This layer provides network services to applications such as email, file transfer, and web browsing. So it's the layer that users interact with most. All right, so we have one last video here that's going to talk about communications via routers.
My name is Lynn Root. I am a software engineer here at Spotify, and I'll be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. How is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there is no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many, many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet, a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it will be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the Internet Protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly, horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend, TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgements of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices or routers along the internet help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
So as an engineer, sometimes, actually, most of the times, communications don't always work right away. And because of that, we have to dig into the packets to see what's going on. A typical tool that we would use is called a network protocol analyzer. The one shown here is by Wireshark. And what this allows you to do is capture back and forth packets of information and kind of decode all of the ones and zeros into something that makes sense. So the example I've got shown here is a DMP3 conversation between 2 devices. I won't go into too much detail about all of this, but I wanted to point out a few items that we've discussed so far. So what we can see here is that this packet is IP utilizing Internet Protocol version 4, which has a source address of 10.33.22.37 and a destination address of 10.33.22.38. We can also see in the transport layer the TCP destination, so Transmission Control Protocol, TCP. It's port 20,000, which is your default port number for DMP protocol. And within your DMP packet, you now have a source and destination address So the Ethernet packet has made it to the correct device. It's told the device it's TCP port 20,000, and now it's communicating to the application layer that I am DMP address 0 and I want to talk to DMP address 1 and would like to request all its class 1, 2, 3 and class 0 data. So the device will then process all of that information and respond with the data. So in this example, the device is responding with 75 binary bits of information, with 0 being a value of 0, 0.1 being a value of 0, and point number 2 being a value of 1, and so forth. So again, just this is what the computer sees when we take a capture. It's not very informative, but we use this Wireshark to decode the information and figure out what's going on. The last couple of slides here, I just wanted to kind of show you how the devices are configured for read-write requests. So the first picture here is how you would configure the RTU for a read request. So we can see right off the bat, the transport protocol is TCP. The IP address is 10.33.22.38, and it's using the IP port of 20,000, which is DMP. Within the DMP section, we have a client DMP address of 0 and a server DMP address of 1. Your integrity poll is your class 0 polling, which is basically the command for sending all of its information to the requesting device since the last time it asked for it. In this case, we can see the RTU sending an integrity poll every 2,000 milliseconds or every 2 seconds. Next, you've got class 1, 2, 3 polling period. So you can set up your information to be in any class that you want, which allows you to prioritize the information. In this case, we aren't concerned with individual class data, so we set it to 0, and we'll just get the info we need on the next integrity poll. On the right, we can see the configuration for what each binary input point is. So for example, the motor operated switch status for switch 201 is binary in 2, and the switch status for switch 202 is binary in 5. The last slide shows the configuration needed on how to respond to a read request. So this would be how the RTU responds to the SCADA server at the ECC. We can see all the same initial information with the IP port of 20,000 establishing the DMP port, remote client IP address of 10.33.22.37 with server DMP address of 1 and client DMP address of 0. The major difference here in communicating with the ECC is the map. So the map specifies the one-for-one information that the RTU is sending over. And in this example shown here, we can see that within the SCADA map, programming establishes that the ECC point 1 is the 89A status of the M201 switch, and point 2 is the 89B status of the M201 switch, and point 3 is the DNO on status of the M201 switch, and so forth. So this concludes today's presentation, and just wanted to thank everyone for listening in and learning a little bit about SCADA. Thank you.